Hello everyone and welcome. So in this chapter 4 lecture, we're going to be taking a look at how we describe a solution quantitatively. And of course we do that by looking at its concentration. Concentration is what we're looking at here. Now, when we talk about quantities of substances, normally it's very easy to describe how much of a substance we have by using, say, the mass of that substance tells you how much you have. But that doesn't work for solutions because a solution is not a pure substance. A solution is a mixture of solute and solvent. So if we weigh a solution, that doesn't tell us how much solute's present, and it doesn't tell you how much solvent's present. And so we use instead concentration because, well, ultimately concentration, all right, indicates what? The proportion of solute and solvent present in that solution. As it turns out, since a solution is a homogeneous mixture down to the molecular level, all right, well, the proportion of solute and solvent is the same throughout the entire solution. So it doesn't matter if you drain out some solution from the bottom of a container or you scoop out some solution from the top of the container, the concentration is the same whether you get the solution from the top or the middle or the bottom. Okay. Now, how do we express solution concentration? Well, it turns out there are many different ways we can express solution concentration. So what are some examples? Well, of course, the big one is molarity. It's one of the ones that we're going to be focusing on heavily in this chapter, but it's certainly not the only way. You can express concentration using molality, or there's even something called normality. Wow, a lot of alities over here. Molarity, molality, normality. Okay, but yet again, there are more methods. We can indicate the concentration of a solution by taking a look at its percent by mass, or even by taking a look at its percent by volume. Another method of determining or expressing the concentration of a solution is to look at something called its mole fraction. And still other ways to express concentration include things like parts per million or even parts per billion. Parts per million or parts per billion. You might know these as ppm or ppb. Well, that's a lot of different methods here. What are the methods we're going to focus on in this chapter? Well, we're going to largely focus on molarity, so check for molarity, and percent by mass. That's what we're going to be covering in chapter 4. Turns out that many of these other techniques you won't get to until, well, another chapter, another course. So molality and normality won't be introduced until you get to Chem 12. Okay. Mole fraction. Mole fraction is rather interesting. Mole fraction is a concentration term used almost exclusively for mixtures of gases. So earlier we found out that gases mix homogeneously, which means that a mixture of gases is technically a solution. And well, we use mole fraction to express the proportion of each gas in a mixture. So let's note here that this is for gas mixtures. And as it turns out, we're going to be covering gas mixtures in chapter 5, so mole fraction is coming soon. Meanwhile, concentration terms like parts per million and parts per billion are almost exclusively used for very dilute solutions. So, very dilute solutions. Okay, so having introduced a variety of terms that we use to express concentration, let's focus on the ones that are important: molarity and percent by mass. So scrolling down here, let's start with solution molarity, which is also sometimes called molar concentration. Okay, let's get a new colored highlighter. Let's go with traditional yellow. So molarity is our first one here. And how is it described? All right, well, it is defined as the mole amount of solute per liter of solution. Well, I can write this in the form of an equation, and that is that the molarity of a solution is simply equal to moles of solute moles of solute over the solution volume. Solution volume, where we always have that solution volume in units of liters. Well, this means that the units for molarity will be what? Well, the units are in moles per liter, moles per liter. Or sometimes we use, all right, the symbol capital M as the units for molarity. The symbol is actually the symbol for molarity itself. We use that symbol interchangeably with the units moles per liter, are the units that we have here. We can rewrite this expression for molarity in a neater, more simplified equation. And of course, that would be that M, the symbol for molarity, equals moles of solute. Now, we typically use an N for the symbol for moles, moles of solute, over V being the solution volume, where this is often called the molarity equation. So I'm going to just circle it. Yay for the molarity equation. And let's put little stars around it because yay for molarity. Okay, well, let's unpack what molarity means in a little bit more detail. Let's suppose we come to our lab and we have a bottle of some chemical solution reagent maybe sitting in the hood. And let's suppose the label on this bottle, let's use a blue pen here, is 0.42 big M, and this is a C6H12O6 aqueous solution in the bottle, where of course that is our old friend glucose from earlier examples. Okay, well, let's start with what's in the bottle. What's in the bottle is a mixture of a solute and a solvent. So what's the solute? Well, the solute is C6H12O6. That is the solute. Now, what's the solvent in this bottle? Well, it is an aqueous solution, and that tells you right away that water is the solvent. So water is the solvent. Now, together, the solute and the solvent give us our solution. And of course, the solution is represented by C6H12O6AQ, which indicates that the solute and the solvent are mixed together to produce that solution. So that's the what's in the bottle. Okay, now let's take a look at the quantitative information. Well, the quantitative information is its molarity concentration, 0.42 big M. All right, big M is said aloud as molar. So this is a 0.42 molar solution of glucose. Well, 0.42 molar could also be written as 0.42 moles per liter. Moles per liter. Because molar and moles per liter are interchangeable as units. Okay. Well, let's unpack this even further. What does this mean? It means quantitatively that there are 0.42 moles of what? Of glucose, which is the solute of C6H12O6 in every 1 liter of the whole solution. Okay, this many moles of solute, there's our solute, in this much solution. Now, this is a fixed proportion of amount of solute, fixed proportion. Whoops, I didn't mean to erase that. Let's just rewrite that here. C6H12 moles. So this is our fixed proportion of the amount of solute to the amount of solution. And this proportion does not change. So for example, if I poured out half a liter of solution, not a whole liter, half a liter, well, how many moles of glucose would be present? Well, it would be half the amount of glucose. It would be 0.21 moles of glucose in half a liter of solution. And if I double the amount of solution to 2 liters, I would have double the moles of glucose present. I would have 0.84 moles of glucose, all right, in 2 liters of solution. So this is how we can think about that molarity concentration right there that we have. All right, these quantities are our fixed ratio. This is the fixed proportion here. Fixed proportion. Okay, well, there is our look at molarity concentration. I said the other concentration expression we're going to look at in this chapter is percent by mass. In particular, what we're going to be looking at is percent solute by mass. And as it turns out here, percent solute by mass is the mass of solute in grams per 100 grams of solution. So in equation form, the way we determine the percentage of solute in a solution is we would need to know the mass of solute that is present. And this would have to be divided by the mass of the entire solution, the solution mass. Now, these would have to be in the same units so that the units cancel out, and this is a percentage, so it would be times 100, and this is how we would obtain the percentage of a solute in a particular solution. There's really no way to make this a smaller, neater formula, so I'm just going to circle it and star it. Yay for percent by mass. Okay, so once again, let's take a closer look at that definition, percent solute by mass in a solution. So we come to the stockroom and pick up another bottle of a solution, and it's labeled maybe, let's write 12% NaOH AQ is the label that we find. So let's again start with what? What's in the bottle? Well, there's a mixture, and that mixture is sodium hydroxide, which is the solute, along with, well, once again, all right, we see that AQ, and that tells us the solvent is water as our solvent. And together, they make a solution, which we represent as NaOH AQ. The two are now mixed together in the solution. Okay. Now, that's the what. Now, let's take a look at the quantitative information. And the quantitative information is this 12%. Okay, now what does that 12% tell us? Well, it tells us the proportion of solute to solution present in this bottle. What it tells us is that there are 12 grams of NaOH, which is the solute, in every 100 grams of solution. So what we have is the proportion of solute, mass of solute in grams per 100 grams of solution. And once again, this represents the fixed proportion of solute to solution. Fixed proportion. So if I double the amount of solution, if I take 200 grams of solution out of the bottle, well, 200 grams of solution will contain 24 grams of sodium hydroxide. If I only take 50 grams of solution from the bottle, well, how much sodium hydroxide will be in that 50 grams of solution? Well, half, just 6 grams of sodium hydroxide will be present. Okay. So now we've taken a look at percent solute by mass and molarity. Let's now put this into practice by doing a number of problems. So let's take a look at the first 5 problems that we're going to work through to practice doing concentration problems. So I'm going to scroll down to our examples. So here's the first example from the chapter 4 ice. Number 1. It says here that a solution is prepared by mixing 35 grams of solid calcium chloride with 271 grams of water. The resulting solution has a density of 1.07 grams per milliliter, and we're asked to do 2 things. First, to get the percent by mass of calcium chloride in the solution, and second, to get its molarity concentration. All right, so let's know what we have here. So we've got calcium chloride and water. And, oh, it's a horrible ampersand, huh? Let's do that over here. So we have these two substances. Now, what are their roles in this problem? Well, it's important to realize that the calcium chloride, of course, is the solute, and water, let's make it a different color here, is the solvent. There we have it. Okay. And, well, we know the quantities. We know that we're mixing 32 grams of calcium chloride together with 271 grams of water. Now, what happens when we mix these substances together? We make a solution. We make calcium chloride aqueous. And this is our solution. And let's envision our solution over here. Our solution is, well, it's mostly water. Mostly water. And within the water, we have our separated particles, right? So let's put little dots in here to represent that something is dissolved in the water. Yes, I've drawn better beakers in my lifetime, I'm sure. There we go. There's our solution. Now, we have some information about the solution we created, namely its density. So let's note that the density of this solution is 1.07 grams per milliliter. Okay, well, let's start with what we need to figure out. In part A of this problem, we'd like to get the percentage of calcium chloride in the solution. So let's work out percent calcium chloride, which happens to be the percent solute by mass. Well, if I want the percentage of calcium chloride, I need the mass of solute, which we have. It's 32 grams of calcium chloride over, well, what does it go over? Well, it goes over the mass of the solution. Now, we don't have the mass of the solution given to us over here. We have its density, but not its mass. So how are we going to get its mass? Well, the mass of the solution would have to be the combined mass of the solute plus the solvent. So 32 grams of solute combined together with 71 grams of water will give us the total solution mass, which is 303 grams. So this is the number that we're going to put in the denominator of our calculation. So on the numerator, solute mass. In the denominator, solution mass. Don't put the solvent mass there. It's not 271 that goes here. And of course, times 100, because this is a percentage. And well, I plugged and chugged this out, and I got a percentage of 10.6% calcium chloride in that calcium chloride solution. Now, part B of this problem wants us to figure out the solution molarity. Now, the solution molarity is given by the formula moles of solute. Now, our solute is calcium chloride over the volume of the entire solution. So how are we going to work this out? Well, let's start with moles of solute. We can get moles of solute from the supplied mass of the solute. The supplied mass of the solute was 32 grams. We can convert that to moles using the very happily supplied molar mass in the problem. So times 1 mole per, well, up there in the problem it tells us the molar mass is 110.98 grams per mole. And when we do this, I end up getting the moles of calcium chloride to be 0.288 moles. Now, we're also going to need the solution volume. Not the solvent volume, the solution volume. So how are we going to get that? Well, we know that density is equal to mass over volume. And so we can use the density equation to solve for the volume, which is that volume of the whole solution must be equal to the mass of the solution over its density. Well, we have the mass of the entire solution, which is the combined mass, of 303 grams, and the problem gave us the density as 1.07 grams per milliliter. So dividing this, I get 283 milliliters. But wait, you say, isn't the volume term supposed to be in liters? Yep, it is. So converting this to liters, it's 0.283 liters. So now, all we got to do is plug and chug this problem out. We've got 0.288 moles of calcium chloride per 0.283 liters of solution. And in the end, I ended up getting a molarity concentration pretty close to 1.02 moles per liter. Or we could write this answer as 1.02 and use the big M. So let's just circle our final answers. Here's the final answer for the percentage, and we can write it either one of these ways as our final answer for the molarity concentration of the solution. Note that it's really important to distinguish between solute, solvent, and solution when you plug and chug and do these problems. Okay, 1 down, 4 to go. Let's take a look at number 2. So number 2 here says concentrated hydrofluoric acid has a molarity of 22.6 big M, that's moles per liter, and a density of 1.13 grams per milliliter. And in this problem, we're asked to express the concentration of the hydrofluoric acid, all right, as a percent HF by mass. Okay, let's draw a little picture here. So let's get back my pen. Okay, that's a slightly better beaker, slightly. And, well, we're talking about hydrofluoric acid. Now, hydrofluoric acid is HF dissolved in water. Okay. So, hydrofluoric acid is HF aqueous. HF aqueous is what we're working with here. Okay, what do we know about this acid solution? Well, we know its molarity concentration. It is 22.6, and I'm going to write it in its formal units, moles per liter. And we also know the density of this solution, 1.13 grams per milliliter. Okay, well, we don't want to express the concentration of our solution in moles per liter. We'd like to express it as a percentage by mass. How do we do that? Well, let's think about what this molarity concentration actually means. It means that there are 22.6 moles of solute. Now, what's the solute in an HF aqueous solution? Well, it's HF is the solute. What's the solvent? It's water. But all right, this concentration term tells us there's 22.6 moles of HF per 1 liter of solution. Okay. So when we express it or draw it out this way in long form, what we now have here are moles of solute. And per 1 liter of solution represents the solution volume. And these are the quantities we're going to use in order to get the percentage of HF in this acid. Now, if I want to calculate the percentage of HF in the hydrofluoric acid, well, what's that going to be? Well, it's going to have to be the mass of HF divided by the solution mass times 100. So how are we going to get the mass of the HF and the solution mass? Well, we can get the mass of the HF from the moles of the HF. So let's do that. So the mass of the HF is going to be obtained from those 22.6 moles of HF. And to convert moles to mass, well, we multiply it by the molar mass of HF. The molar mass of HF, 20.01 grams per 1 mole. And when I plugged and chugged this out, I ended up with a mass of 452 grams of HF. And if I want to get the solution mass, well, guess what? I'm going to have to use the solution volume and the solution density. So I know that the mass of the whole solution is going to be equal to the density of the solution multiplied by its volume. Or the density of the solution, 1.13 grams per milliliter times. Now, let's be careful. This volume is 1 liter, Well, 1 liter is the same as 1,000 milliliters. So using 1,000 milliliters here, so milliliters cancel milliliters, what do we end up with? Well, we end up with 1,130 grams of solution. Well, I'm going to take these values and plug them back into my formula for the percentage of HF. So over here, going back to the calculation, 452 grams of HF over 1,130 grams of the solution times 100. And in the end, I get that the final solution has a concentration of 40% HF by mass. So really it was about understanding how to think about that molarity concentration as a ratio and what ratio it was telling us before we could pull out the information we needed to get the percentage of HF in this solution. Okay, let's move on to the next problem. Number 3. So number 3 says a reaction requires 2.40 times 10 to the negative 2 grams of Li3PO4. That's lithium phosphate. We're asked what volume in milliliters of a 0.141 molar lithium phosphate aqueous solution should you use? Okay, so let's again draw a little picture here. Let's put a sample of lithium phosphate aqueous solution in a graduated cylinder. So here's my really, really sad looking graduated cylinder with a terrible meniscus. You can do better, of course. And let's put the little dots in because there's stuff dissolved in the water. And what is the solution that we have here? It is Li3PO4 aqueous. What's the solute? Lithium phosphate. What's the solvent? Water, because it's an aqueous solution. Now, what's our goal? We want to know the volume of this solution. We want to know the volume of this solution. So we know the molarity equation says that molarity equals moles over volume. And so if we want to figure out volume, well, this equation is going to have to be rearranged. And that is that the volume of a solution must be equal to moles over molarity. And let's be careful. Moles of what? Moles of solute, where the moles of solute would be lithium phosphate. So we need 2 bits of information, all right, to solve for the volume of the solution. We need moles of lithium phosphate and molarity. Well, the molarity is provided for us in the problem. We're told that the molarity of the solution is 0.141, and let's write it in the correct units, moles per liter. So we have the molarity. Check. Okay, so we just need the moles of lithium phosphate. Now, the problem doesn't give us moles of lithium phosphate, but it does give us right here the mass of the lithium phosphate. So all we need to do is take that mass and convert it to moles. So our moles of lithium phosphate can be obtained by taking that mass, 2.40 times 10 to the negative 2 grams, and simply converting it using the supplied molar mass, 1 mole per 115.79 grams. And when we do this conversion here, I ended up getting 0.0002. Oops, that's not right. Let's fix that. First part's right. Got all those zeros. 207 moles. Okay, so now we have moles of lithium phosphate. It's now plug and chug, so let's plug and chug it out. The volume is equal to 0.000207 moles over 0.141 moles per liter. So from a unit perspective, what happens? Moles cancel moles, which means the units we're going to end up with are what? Oh, right, liters. And in liters, the value I ended up getting was 0.00147. But the problem doesn't want us to solve for our answer in liters, it wants milliliters. And so converting to milliliters, we multiply by 1,000, we're going to end up with 1.47 milliliters is the amount of solution we need to use. Okay, so this was a fairly straightforward example where we just had to rearrange the molarity equation and solve for volume using the supplied molarity and our obtained mole quantity of solute, which we got from the mass of the solute. Okay, just pay attention to units and you're all set. Okay. Next problem. Don't worry. 2 more to go. Obviously, they're a little bit harder. So, number 4 says, which one of the following solutions contains the greatest number of ions? And we have two solutions. Solution A, which is a solution of sodium sulfide, and solution B, a solution of iron 3 nitrate. By the way, this is an old multiple choice test problem from a few years ago. So let's note what the solutions are. So we've got a solution of sodium sulfide. And let's put the other solution over here, a solution of iron 3 nitrate as the two solutions we're looking at. So let's start with the information we know about these solutions. Well, for starters, we know the molarity of both of these solutions. The molarity of the sodium sulfide solution is 0.40, and let's write it in the appropriate units, moles per liter. And for the iron nitrate, its molarity, we're told, is 0.75, and again, I'm going to write that as moles per liter. The second thing we know about the two solutions is their volume. We're told that the volume of the sodium sulfide solution is 20 milliliters, while the volume of the iron nitrate solution is 10 milliliters. So all I've did is write out the information. Okay. I should note that when we do molarity problems, we don't like using milliliters. We like our volumes to be in liters, so I'm going to rewrite this as 0.0200 liters, and I'm going to rewrite this as 0.0100 liters. I just did the conversion by dividing by 1,000 very quickly in my head. Now, if we know the molarity of a solution and the volume of a solution, there's only one term missing in the molarity equation, and that is moles. So let's, of course, remember that molarity equals moles of solute over solution volume. Now, for both of these solutions, we know molarity and we know volume. And so what we can solve for is moles of solute. Now, how does this equation rearrange? Well, moles of solute would be equal to molarity times volume. Okay, well, let's do that. Let's solve for moles of solute in both of these solutions. Now, what's the solute in the sodium sulfide solution? Why, it's sodium sulfide. Sodium sulfide is the solute, water is the solvent. So let's get moles of sodium sulfide simply by multiplying the molarity and the volume together. The units are all good. Note that liters cancel with liters, and we're going to end up with moles. And I already did this plugging and chugging. I ended up with 0.0080 moles of sodium sulfide. Over here for the iron nitrate, moles of iron nitrate, iron 3 nitrate. Again, take the molarity, multiply it by the volume, liters cancel liters, and I ended up getting 0.0075 moles of iron nitrate. Now, here's where we now need to put our knowledge of quantity with the knowledge that we learned in a previous lecture about the qualitative nature of different substances when we dissolve them in water. Turns out that sodium sulfide and iron 3 nitrate are strong electrolytes. Why? Because they're soluble salts. They're both strong electrolytes. They're soluble salts. Now, what does a strong electrolyte do in water? Oh, it splits 100% apart into ions. All right, these are actually solutions of ions. So if you think about it, all right, if we have one sodium sulfide in solution, all right, that one sodium sulfide is actually broken apart in solution into 2 sodium ions and 1 sulfide ion. That's how it actually exists in solution as separated ions. Meanwhile, for every 1 iron nitrate that dissolves in water, what we really end up with are separated irons and nitrates. As it turns out, we get 1 iron for every 3 nitrates. So we have separated ions in solution. Note that when sodium sulfide breaks apart, for every 1 sodium sulfide, we get 3 ions total. And for every 1 iron nitrate that breaks apart, we get 4 ions. Now, in this problem, we're not interested in the moles of solute. We're interested in the amount of ions. So how can I get moles of ions? Well, the moles of ions are simply going to be 3 times the moles of solute. In other words, I'm going to take my original amount of solute calculated, and there are 3 ions produced for every 1 sodium sulfide that breaks apart. But in the iron nitrate solution, if I want to get moles of ions, I'm going to take my moles of iron nitrate, which I already calculated, but in this case, we get 4 ions produced for every 1 iron nitrate that splits apart. And so for the sodium sulfide solution, when I calculate this, I ended up getting that there are 0.024 moles of ions floating around in that solution. Whereas for the iron nitrate, when I multiplied by 4 over 1, I ended up getting 0.030 moles of ions are floating around in the solution. Now the problem asked for which of the following solutions has the greatest number of ions. Well, that would be this one over here. Greatest number of ions. All right, because 0.030 moles of ions is clearly a bigger number than, all right, for the sodium sulfide, which was only 0.024 moles of ions. And so as a multiple choice test question, all right, your answer would have been B. This one has more ions floating around in that solution. So qualitative plus quantitative together in the problem to make it a whole lot more interesting, which is now going to take us to that last problem right over here, which is the big one, and that's number 5. So 25 milliliters of 0.321 molar iron 3-chloride solution is mixed with 30 milliliters of 0.41 molar calcium chloride solution, and we would like to calculate the concentration of chloride ions in the resulting solution. Oh boy. So this is definitely a job for drawing a picture to help you think about the information you've been provided with. So what are you doing? You're mixing 2 solutions together. Mixing 2 solutions together. What are the 2 solutions you're mixing together? Well, one of them is FeCl3 aqueous, and the other one is CaCl2 aqueous. Okay. Now, both of these solutions are solutions of a strong electrolyte. So in the iron solution over here, in the iron solution, well, what's in this iron chloride solution? Well, we have water because it's an aqueous solution, but we also have separated ions. We have Fe plus 3 cations. We have Cl negative 1 ions, all floating around in the water. So when we dump this solution into the beaker, what are we really dumping into the beaker? We're putting water into the beaker, we're putting chloride ions in the beaker, and we're putting iron cations in the beaker. Now, when we add, let's use a different color here, calcium chloride solution to the beaker, well, this is also a strong electrolyte. So what are we actually dumping into that beaker? Well, again, we're adding water to the beaker, but we're also adding separated ions, calcium and chloride ions. So what's going in here? Well, we're putting some calcium ions in here, some chloride ions in here, and of course some water in here. So what do we end up with? Well, we end up with a solution which is mostly water with a bunch of different ions floating around in that solution. What ions are floating around in here? Well, we're going to have some Fe+3 cations floating around in here. We're going to have some calcium ions floating around in here. And of course, we're also going to have some chloride ions floating around in here. Now, of all the ions floating around in this solution, the ones that we're interested in are the chloride ions. And that's because the problem asks for the concentration of chloride ions in the resulting solution. Okay, and that of course should be a molarity concentration. I probably should have had that a little bit more explicit. I'm going to leave a little space, and I'm going to note that what we're after in this problem is to get the molarity of the chloride ions in the solution. Now, how are we going to get that? Well, the molarity of the chloride ions in the solution would have to be equal to the total number of moles of chloride present in that final solution over the total solution volume of that final solution. Okay, now let's start with the moles of chloride that are in the final solution. Well, where did those moles of chloride come from that are in the final solution? Well, some of the chloride came from the iron 3 chloride, and some of the chloride is coming from the calcium chloride. So we could say that the total moles of chloride would be moles of chloride from the iron chloride solution plus the moles of chloride that came from the calcium chloride solution. Okay, that's going to be our numerator. And in our denominator, well, we need the total solution volume. Well, the total solution volume would have to be the combined volume of the iron chloride solution and the calcium chloride solution. So let's just write that this is going to be the combined volume of the two solutions. Okay, well, now we've thought it through, we're now going to need to get some numbers. So let's take a look at the information we have about the iron 3 chloride solution. And we note that we have its molarity, 0.321 moles per liter. We also have its volume. The volume is 25 milliliters, but we don't like milliliters, 0.0250 liters. Okay. We have a similar set of information for the calcium chloride solution that we're dumping in. We have the molarity of this solution, 0.412 moles per liter, and we have its volume, 30 milliliters, or converting 0.0300 liters. Now, in the previous problem, we saw that if we know the molarity and volume of a solution, what can we calculate? Moles of solute. So let's do that for iron 3 chloride. Moles of iron 3 chloride, which are the solute, is the molarity of the solution times the volume of the solution. Since the units are already good to go, liters cancel liters, and I ended up getting 0.008025 moles of iron chloride are the number of moles of solute in the first solution. In the calcium chloride solution, calculating moles of calcium chloride, again, molarity times volume. I plugged and chugged the numbers, 0.412 times 0.0300, and I ended up getting 0.1236 moles of calcium chloride. But we're not interested in anything but chloride. The only part that we're interested in chloride. So let's notice that in iron 3 chloride, there are 3 chlorides for every 1 iron chloride, which means that moles of chloride would simply be equal to 0.008025 of the moles of iron chloride times 3. It's really 3 over 1. 3 chlorides for every 1 iron chloride. Or, when I plugged and chugged this out, 0.0 24, we'll worry about sig figs later, 2407 moles of chloride. Okay. Now, in contrast, for the calcium chloride, we see that there are 2 chlorides for every 1 calcium chloride. And if we want to get moles of just the chloride here, it's going to be 0.01236 moles times 2, or 2 over 1. And in this case, 0.02472 moles. Okay, well, now we need all the information to complete the problem and get the molarity of chloride ions in that final solution. Whoops, did not mean to do that. Let's move this in the right direction, and that is up. So coming back here, well, we're going to take the moles of chloride from the iron chloride solution, 0.02407, and add it to the moles that we worked out from the calcium chloride solution, 0.02472 moles. And we're going to divide this by the combined volume, and we need to use liters. Well, the volume of the first solution was 0.0250 liters, and the second solution, 0.0300 liters. Or, adding these values together, 0.048795 moles of chloride in total in the final solution. And that final solution has a total volume now of 0.0550 liters, which means, drum roll please, the final solution concentration of just the chloride ions, 0.887 moles per liter, or of course we can write this as 0.887 with the big M. So that's our review of solution concentration, all right, with all of the follow-up examples. So we're in great shape. Keep at it. Start practicing your problem solving from the Chapter 4 end of chapter problems so that you're keeping up with this material. Okay, I hope you guys are all doing well. I know this is difficult. It's difficult for me too. Hang in there and take care. Bye, everyone. Talk to you soon.